Now let's see, I've got a pointer here. Yeah, it points, okay. So, I'm going to just mention again this very cute way that Rodriguez found for generating families of orthogonal polynomials. It's really quite remarkable. First, you pick any weight function you want, and then you pick a function q that vanishes at the endpoints of your interval. And I guess if w is going to be a weight function, then you want it to be positive on the interval. And you then compute the ENs to satisfy some normalization constraint. And these formulas then automatically give you functions Rn that are, or polynomials Rn that are orthogonal with respect to the weight function w on the interval from a to b, as long as q vanishes on the endpoint. Now, I actually bought a clicker that is supposedly, indeed. Now I'm wondering, can I get it to page up a little bit? No, I think maybe that was too much. Anyway, there are many, many examples that we went through last time. Jacobi polynomials, and these, and then if you set alpha equal to beta, you get the Gegenbauer ones, and then the Chebyshev ones, and you set both alpha and beta equal to 0, you're back at the Legendre polynomials. So that's quite really remarkable. What you also have here are the Hermite polynomials, and there the weight function you see is an exponential of e to the x squared, e to the plus or minus x squared. And and they satisfy this differential equation, and they're generated. Wow, I don't know if this clicker is what it's hooked up to be. It's just a little excitable. So as I was saying, the Hermite polynomials are like that, and then the Legendre polynomials are these ones, and they occur in the radial function of the hydrogen atom, radial eigenfunctions of the hydrogen atom. That is to say, the bound state eigenfunctions. There are also continuum eigenfunctions, which correspond to, say, an electron scattering off a proton and then going off to infinity. So those are the Legendre polynomials. The Hermite polynomials are also the ones for the harmonic oscillator. Now, what I want to switch to now are the angular functions that are associated with Legendre polynomials. And so in particular, if we just go to, first of all, the Laplacian is separates in spherical coordinates, and let me just get my notes in the right place. And if the system has no dependence, whoops. System has no dependence on the angle phi, then we say it has azimuthal symmetry, and so then the appropriate function is just a product of a radial function and a function of the polar angle theta, and this will be a solution of Helmholtz's equation if the functions r and theta satisfy these equations. So there's, that's the equation for r, and the one for theta is Legendre's equation. And we can see that because if we set theta L of theta equal to PL of cosine theta, this actually gives us back Legendre's equation in self-adjoint form, expressed in terms of the variable theta. And for k greater than 0, the solutions that are finite at r equal to 0, that now I'm talking about this equation, these are the spherical Bessel functions, which are given by Rayleigh's formula. And this Rayleigh formula is quite nice, and it shows you how simple the spherical Bessel functions are. So you must think of them as really nice functions, whereas the cylindrical Bessel functions are quite a bit more complicated. And so then the general azimuthally symmetric solution of Helmholtz's equation, and let me get back to Helmholtz's equation just so we can remember what it is. It is minus Laplacian f equals k squared f. And if the solution is finite at the origin, then we take a linear combination of the Legendre polynomials and the spherical Bessel function. We get this function f. On the other hand, if the function can be infinite at the origin, then we bring in the Neumann functions, which are also quite simple, but they are infinite at the origin. And so the general solution in that case, and this sometimes is used for functions for the case where the function you're looking for, the unknown function f, or the function you're trying to represent f, the solution f, is infinite at the origin. Another case is where the origin is not in the problem, and so you don't care whether it's infinite or not at the origin. If, for example, you're solving for the function f outside of some sphere about the origin, then of course you don't care whether the function is, whether f is infinite at the origin, and so then you must use both the spherical Bessel functions and the spherical Neumann functions, and then just the Legendre polynomials. This again is for azimuthal symmetry. By the way, I forgot to ask if anybody's starving. Is anybody starving here? No? Okay. When k equals 0, the Helmholtz equation minus Laplacian f equals k squared f reduces just to Laplace's equation, namely that the Laplacian on f vanishes. And that's this equation. So now if I advance that a little bit, the radial equation with k equal to 0 then is 984 d by dr of r squared drl dr equals ll plus 1 times r to the l. So what you do with k equals 0, so you set RL equal to r to the n and substitute into that equation, and then you find that nn plus 1 must equal ll plus 1. And an obvious solution is n equals l, but another solution is n equal minus l plus 1. And so the general solution is of this form. Of course, these are infinite at the origin, but once again, if the origin is not in the region you're solving for, then it doesn't matter. and you must include these functions. Or if you're solving for a potential that might be infinite at the origin, then of course you do include them. Now if we go to 2 dimensions, what we find is that the Helmholtz equation, I see I don't have the most recent version of my notes on this paper, on this computer. So let me remind you, what we're talking about here is the, again, Laplace's, the Helmholtz equation, and that's minus grad squared f equals k squared f. So back in section 7.3 we saw that it separates in cylindrical coordinates, and so then we can write f as equal to some rho of rho, some phi of phi, and times some z of z. And if that shouldn't be alpha equals 0, that's supposed to be k equals 0, so that's a typo in the book. So if k equals 0, then you're down to minus Laplacian squared of f equal to 0, and you're back with Laplace's equation. And now if the function f is also independent of z, then there are simple solutions, and in this case your solution looks very much like the one we had before, but it's slightly different. Instead of LL plus 1, we just have m squared, and that's because we're in cylindrical coordinates. And we can take the function phi to be e to the im phi, and so that's a linear combination of sine and cosine of m phi. Now here, the question is the whole interval from 0 to 2 pi physical? If it is, then m has to be an integer, because the function phi has to be single valued. On the other hand, if you're dealing with a problem in which part of the, in other words, if you're dealing with a problem in which you're trying to find the function outside of a certain wedge, then m does not need to be an integer, and so you have to allow for m to be not an integer. In any case, if m is an if m has to be an integer, then we set rho sub m equal to rho to be n, and we solve, and we get this equation, and that means that n has to be plus or minus m. And so then the solution looks like this. Actually, I'm just wondering here whether I should have included e to the minus IFB. All right, let me think about that. I'll send you guys an email tonight about that. I just want to think about it. It didn't occur to me until just now. Let's go to spherical coordinates. Then we know that Helmholtz's equation, or the Laplacian, effectively separates in spherical coordinates. And so we get a radial function depending on k and l, and azimuthal function theta of L and M, and then an angular function phi, or an azimuthal function phi. And this will be a solution if R is a linear combination of spherical Bessel functions, and if phi is e to the im phi, and if theta satisfies this associated, this equation, which is called the Associated Legendre equation, and the solutions are the associated Legendre polynomials. They're polynomials not in x, but not in cosine of theta, or x equal to cosine theta, but they're polynomials in terms of cosine theta and sine theta, or equivalently, polynomials in x and in square root of 1 minus x squared, which is what the sine would be if x is the cosine of theta. And so these are solutions of the separated theta equation, which is that equation 9.3. Here, I guess I can see if I can do this without advancing the text. And if we set x equal to cosine theta, then the self-adjoint form of this equation is this. And we see the weight function is 1 minus x squared. These associated Legendre functions are simply related to the nth derivative of the Legendre polynomial. So what we have here is PLM of x is 1 minus x squared to the m over 2 times the nth derivative of the nth Legendre polynomial. And so what we do is we now differentiate this PL of m is then, so the point is that PLM is the nth derivative of the Legendre polynomial, and it's related to the associated Legendre polynomial by this factor of 1 minus x squared to the minus m over 2. So just to check that this is true, what we do is we differentiate this expression once to get the m plus first derivative of the Legendre polynomial. Then we differentiate a second time, and we get the m plus 2 derivative of the Legendre polynomial. And then we use Leibniz's rule to differentiate Legendre's equation m times. And so that's a rather elaborate thing. And what we find is we get this expression here. And now if we substitute for the m plus second derivative of PL and the m plus first derivative of PL and the nth derivative of PL, we put all of them into this equation, we find that the definition 9.5 actually does satisfy the original equation, which was this one, 9.94. So that's sort of a quick derivation of, or verification that this is the right formula. And so what we've got is a sort of extension of the Rodriguez expression, because what we have is that the associated Legendre functions then are this factor, which is basically sine of theta to the raised to the mth power, times the mth derivative of the Legendre polynomial. So it's this expression here. And they're simple polynomials, as I said, in cosine theta and sine theta. And written in those terms, then they're rather simpler. They're sine to the m, the mth derivative with respect to cosine theta, or PL of cosine theta. And now if we use Rodriguez's formula for the Legendre polynomials, then we can write the earlier definition of the associated Legendre polynomial in this way. Namely, the L plus nth derivative of x minus 1 to the L multiplied by x minus 1 minus x squared to the m over 2, and then we divide by that formula that appeared in the original Rodriguez formula. And so this extends the, this Rodriguez formula also extends the associated Legendre polynomial to negative values of the integer m. So for negative m, what we have here is that this radical, this is 1 over 1 minus x squared to the m over 2. And over here, we're just subtracting a certain integer m from L if m is negative. And this formula also tells us that PLM of minus x is, well, there's no effect here, no effect there, but there's a factor of minus 1 to the L plus m. So the parity of the associated Legendre polynomial is minus 1 to the L plus m. This Rodriguez formula, which one gets a lot of mileage out of the Rodriguez formula. What we see here is that it only makes sense as long as L plus m is positive. So what that means is that m can't be less than minus L. So m could be minus L, and then this would be 0. But if m was minus L minus 1, we would have the Rodriguez formula wouldn't make any sense. Let me just remind you that the Rodriguez formula involves the L plus nth derivative. Well, if that's negative, then that doesn't really work. On the other hand, so that gives us this condition that one sees in quantum mechanics, namely that the magnetic quantum number m can't be less than minus L. On the other hand, if m is greater than L, then PLM is given by something more than 2L derivatives of something that at most is a function of x, is polynomial x, and the highest power is x to the 2L. So if you differentiate more than 2L times, you get 0. And so that means that you can't have m greater than L. So the associated Legendre polynomials all have m going in integer steps from minus L to plus L. And those are things that you see in quantum mechanics class. Here you see what the actual reasons are. You can also show that PL of minus m is given by PL of m times this overall factor. And since m occurs only as m squared in the original differential equation for the associated Legendre function, it follows that L of minus m has to be proportional to Ln. So that's why these things are proportional to each other. Under reflections, the parity we've seen is minus 1 to the L plus m. And if m is not equal to 0, then PLM has a power of this square root in it, and consequently it vanishes at x equal plus or minus 1, which corresponds to theta equals 0, theta equal to pi. So these, the PLMs for m not equal to 0 vanish here and there. So now here is the differential equation in self-adjoint form for the associated Legendre polynomial. And what we see is that we've got two parameters here that we might think of as eigenfunctions. L and eigenvalues, L or M. And in fact, both are legitimate, both are eigenvalues, but for a different differential equation, a different problem, essentially. So if you take LL plus 1 as the eigenvalue, then the weight function is unity. And since it's self-adjoint on the interval, the eigenfunctions must be orthogonal on that interval when L and L prime are different. So let me raise this up and show it to you. So in this case, the integral here, I think that's enough. So the integral formula then that shows you that the Associated Legendre polynomials are orthogonal and normalized in this way. They're orthogonal if L is not equal to L prime. Here, M is regarded as a part of the differential equation, or it tells you what self-adjoint system you're talking about. So you have M fixed. On the other hand, you can also say, well, let's regard L as a parameter and M as the eigenvalue. So if we let M squared be the eigenvalue, then the weight function is 1 over 1 minus x squared. The eigenfunctions then are orthogonal for different values of M for fixed L. And they're orthogonal again on this interval minus 1 to 1. And the formula, the orthogonality formula is like this, with the weight function sitting there. So keep that in mind, that there are two different ways of looking at the equation for the Associated Legendre functions or polynomials. So in terms of these Associated Legendre polynomials, and simply the phase factors e to the im phi, you multiply them together, what you get is a spherical harmonic. Here, this capital theta, this funny thing here is capital Greek theta, it is related to the Associated Legendre polynomial by this square root and then this phase factor. I should mention that different authors have used different definitions of the spherical harmonics and of theta Lm, and so occasionally there's a different phase. I think the difference is always just the phase, but who knows, maybe there's something else. Here the phis are written so as to be normalized on and to be orthonormal on the interval 0 to 2 pi. And the big square root in that definition of the spherical harmonic makes the spherical harmonics orthonormal when integrated over the sphere. And the unit of area on the unit sphere, the element of area on the unit sphere is d phi times sine theta d theta. And so that's the orthonormality equation. And now in spherical coordinates, the parity transformation is that the r prime is r, theta prime is pi minus theta. So if we have theta, we go down to pi minus theta, so it goes like that. But phi has to go around. So this point here goes to that, and then rotated by pi to here. And so that's why phi prime is phi plus or minus pi. And so under parity, cosine theta prime is minus cosine theta, and e to the im phi is minus 1 to the m, e to the im phi. E to the im phi prime is minus 1 to the m, e to the im phi. And this factor of minus 1 to the m cancels the m dependence of the Associated Legendre polynomial. So under parity, the spherical harmonics just have a parity of minus 1 to the L. And that's something that you've probably seen in quantum mechanics classes where you say, well, the hydrogen out of wave functions. eigenfunctions have parity -1 to the L, and that gives you various selection rules, which are, of course, important in optics and atomic and molecular physics. Now, the spherical harmonics obviously are complete on the unit sphere, so we can expand any smooth function, and in fact smooth means, some context it means infinitely differentiable. Here I think it's certainly any continuous function, and depending on what we mean by convergence, it could be any square integrable function. Anyway, we can expand them in terms as a series in the spherical harmonics. And then if we use the orthogonality of the spherical harmonics, we can compute the coefficients in this way. And if we combine these two equations, that is to say, if we take this equation and substitute for the ALMs, we get this expression here. And so now what we have is f of theta and phi is f of theta prime phi prime when integrated with respect to this square bracket over the unit sphere. Well, that means that the square bracket is an angular delta function, and it's an angular delta function that cancels this factor of sine theta. And some people abbreviate it as delta 2 of omega minus omega prime, and many people just omit the 2 and the superscript 2. This spherical harmonic expansion of the Legendre polynomials, of the Legendre polynomial PL of n dot n prime, where these n's are unit vectors. The hat means unit vector, of course. And these are the unit vectors whose polar angles are theta and phi and theta prime and phi prime. Well, it is of this form. This is called the addition theorem, and it's derived in the chapter on group theory. So this next topic is just some applications of this that have been important in astronomy and cosmology. This is the map of the temperature fluctuations over the celestial sphere as measured by the Planck satellite. This radiation is the cosmic microwave background. These are photons that have been traveling since the universe became transparent, which was when the temperature dropped enough for atomic hydrogen to be stable. Before that, the atomic hydrogen was either unstable or it was not even an atom, but it was protons and electrons racing around, not paying much attention one to the other. But when the temperature dropped to about 3,000 degrees Kelvin, the hydrogen became transparent. And this, by the way, this period of transition from a plasma that was totally featureless from the point of view of optics, because the photons were constantly being scattered by electrons. The transition from something that was just a blindingly bright, featureless plasma to a transparent universe. This was not instantaneous, and I think, in fact, that the transition, in some sense, was thousands, possibly hundreds, possibly 100,000 years in taking place, going from an opaque plasma to a transparent sky. And what we're seeing here is fluctuations that are of the order of 10 to the minus 5. So the remarkable thing about one of the remarkable things about the cosmic microwave background radiation is that it's all at the same temperature, 2.7255 Kelvin, apart from tiny fluctuations of 300 microkelvin. And you can Google a nice color photo of that. I have black and white here, unfortunately. This Planck satellite, by the way, was at the second Lagrange point, which is in the Earth's shadow, first of all. And you want to be in the Earth's shadow because you're trying to observe radiation that is the photons that have a temperature of 2.7 Kelvin. So if you're in full sunlight, then the detector is blinded by the photons from the sun. And this Lagrange point is 1.5 million kilometers farther from the sun than the Earth. And it's a place where if you put something there moving at the right velocity, it stays at the Lagrange point and goes around with the Earth. By the way, one thing that I skipped when I showed you the picture here is there's something subtracted out. Anybody want to tell me what it is that we subtracted out to get this thing to get the radiation to be the same in all directions? Well, it's the motion of the Earth relative to the cosmic microwave background, which provides an absolute frame of reference for the universe. And that motion of the Earth is partly that the Earth is moving around the sun, but more importantly, the sun is moving in the galaxy, and the galaxy is also moving. And so everything is moving, the Earth is moving at quite a high speed. I forget what the speed is, relative to the, I think in one version, oh my goodness, look at that. Isn't that something? That's strange. It's sort of too bad because that's something that I wanted to show you. Anyway, it's, let me see if I mention what the speed is. Well, I forget. Anyway, we're moving very fast relative to the cosmic microwave background. Fast compared to ordinary Earth velocities. Very slow compared to the speed of light. So what the Planck people did was, well, they did many things, but in particular, they expanded the temperature at different angles in the sky in terms of the spherical harmonics. And then they weren't so much interested in different directions, and so they took a sum over the magnetic quantum number from -1 to L and took an absolute value squared and defined something called C sub L. And then in terms of C sub L, they multiplied by LL plus 1 and got something called D sub L. But if you use the addition theorem, you can see that the C sub L's are actually a kind of correlation function of the temperature in one direction with the temperature in the other direction, weighted by the Helmholtz Legendre polynomial. And so what they found when they plotted d d sub L, let me get to that. I'll draw you a picture of it. Grab another piece of chalk. So what we've got here is d sub L plotted on against L here, and we're going from something like 2 to 2500. And the curve, and here we're going from 0 to 6000. And let me get the maximum here is around, say, 200. And so this thing goes up like this, and then comes down, and then it starts trailing off like that. Well, I'm afraid I did not do that so well to scale. Let me redo this. All right, that's a little better. So what we're seeing here is what is the maximum of the absolute value of delta t, essentially. And this is corresponds to areas that were slightly overdense. And slightly means 1 part in 10 to the 5th, or 1 part in 10 to the 4th. Those pull together the plasma, and so the temperature was somewhat higher. Then here is, so some of those, so what would happen was you had a big area that condensed a little bit and was a higher temperature. And notice that the angles here, this is around 1 degree. And so as we go out here, this is, these are very tiny amounts. I don't have that written here. And these are larger. So this is, for example, 20 degrees, and this is, I'm just guessing here, 0.001 degree. And so the L's go one way, the angles go the opposite way. So this peak corresponds to the first compression, and then an area that was falling in and produced a higher temperature. The radiation pressure eventually pushed that back, and then it then rarefied, and before it started to fall in again, the temperature was lower. So this is a minimum temperature. This is again a maximum temperature, and so on. So that's what the Planck satellite and the analysis by a large team of astronomers and physicists found. And this provided evidence that the universe was either absolutely flat or almost flat, and that let me see if I can remember all the different things that the conclusions. It established, the most important thing was that it established what's called the Lambda-Cdm Model. This is cold, dark matter, and this is the cosmological constant. And this cosmological constant, of course, has caused the expansion of the universe to accelerate over the past over the past 4 billion years or so. And the Planck people were able to determine the original baryon density, the cold dark matter density, and a variety of other parameters. And so it was a really remarkable achievement. And in fact, they were able to, you see, I drew this curve, and I wasn't distinguishing data from theory. In fact, apart from here, the curve of theory and data are almost identical. Now, one aspect of the theory, though, was a parameter that was fitted to the data, and that was the height of the first maximum. So that was just fitted. The other parameters, the other 6 parameters that went in, were also fitted, but once you have, I'm sorry, the other 5 parameters. So this is basically a 6-parameter fit to the data. And the reason for the discrepancy here is that, you see, the prediction of the theory is that on the average, this is what you'd have. Well, we just have one universe to look at, and these are the correlations of the temperatures at very small distances, differences in angle, and there are a gazillion of these in the sky. If you look, there are like 2 points there, 2 points there, 2 points there. But these correspond to big angles, like 20. Well, there aren't that many pairs of big angles in the sky, and so the statistics aren't so good here. Anyway, it's quite an achievement, and what I left out, or among the many things I left out in this discussion, was that one of the ingredients here is that these initial fluctuations were fluctuations at very early times as the universe was expanding, and these fluctuations were caused by simply the uncertainty principle in quantum mechanics. That is to say, quantum mechanically, you expect things to fluctuate, and their models for the way in which things fluctuate gave them allowed them to predict this curve in terms of a couple of parameters. And in fact, now that I think about it, these parameters have to do with, one of the parameters has to do with how the fluctuations vary with frequency. And this is also more or less consistent with inflation, or it's very consistent with inflation, I should say. And the idea with inflation, of course, is that very early in the universe, very early, the known universe was expanding at, was very much smaller, and was expanding at superluminal speed. What was expanding was space. Space was expanding very rapidly because the potential, the idea of inflation is that the potential energy of the system at very, very early times, and here we're talking much less than a microsecond, and in some models like 10 to the minus 30 seconds. So at extremely early times, the density, the energy density was extremely high and was mostly potential. If it was mostly potential rather than kinetic, then that, the equations of general relativity tell you that that would drive a superluminal expansion. In fact, it's not all, you don't really need very much you don't need general relativity to see this. In fact, the idea is that pressure, of course, is minus the partial of the internal energy with respect to volume. And so if you have a situation in which the potential energy is very high and you double the volume, then you've doubled the energy. And so the partial of energy with respect to volume is positive, and so the pressure is negative. An enormously negative pressure causes a violent expansion of the universe briefly until the potential energy goes away and is converted to kinetic energy, which is to say radiation. And the radiation due to the potential energy, the radiation produced when the potential energy became kinetic energy, that's called the Big Bang. And so the model is there was inflation, Big Bang, and then the universe expanded since then. The known physics works from about a nanosecond, when the time is a nanosecond on, known physics more or less works. Before a nanosecond, what we know about physics isn't good enough to really predict what's going on. By the way, one of the leading cosmologists, Joseph Silk, a couple of weeks ago, put on the archive and Nature Astronomy published a paper by the paper he put on the archive, and in that paper he suggests that the universe might be closed, which, frankly, from my point of view, is much more sensible than totally flat. Because totally flat or open means that it's infinite, and it's hard for me to think about inflation occurring on an infinite scale. All right, I think we've pretty much done this chapter then, although you may have questions. We have still about, I think, 20 minutes left. Are there any questions, or shall I go on and start Bessel functions? So, the cylindrical Bessel functions, as I said, are highly non-trivial functions. For any integer and non-negative integer, they're given by this series. And so that's, you know, as you see, it's an infinite series, and it's somewhat complicated infinite series. The first term tells you that if z is very small, and by the way, this is obviously, in fact, it's obviously an entire function of z, because these, you have a double m factorial down here, and consequently, the series converges very rapidly. For small z, what you've got is the first term is dominant, and so Jn of z is basically z to the n over 2 to the n factorial. The alternating series here make the waves that are seen in figure 1. So figure 1 is a plot of some of these. So these are some of the Bessel functions. What we have up here are 0, 1, and 2, and down here we have j, 3, 4, and 5. So you see they turn into, they almost look like sines and cosines as you get to large values of z. On the other hand, if you go to very large z, then you have an approximation like this, and as I said, they look like a trigonometric function, cosine or sine, apart from a 1 over square root of z. and also it's not cosine z, but it's, if it's Jn, then you subtract n pi over 2, and then you always subtract pi over 4. These Jn of z's are entire functions, and they obey Bessel's equation, which, not in self-adjoint form, looks like this. They have a generating function, which is given by, which is this very simple expression here, and it's, I'm always amazed by these generating functions. You have a generating function that you can write down in just a few seconds, and that generating function gives you an infinite series of all of the Bessel functions. And I mean, that's just amazing. All of the cylindrical Bessel functions for integer n. We'll talk about non-integer n later. And you can derive from the generating function both the series expansion and an integral representation. And in particular, the integral representation here is that Jn is a cosine, Jn of z is a cosine of z sine theta minus n theta d theta integrated from 0 to pi. So that's quite a remarkable expression. If I'm not mistaken, Glauber used either this formula or one like it in a paper he wrote many years ago on scattering theory. And what he was saying was that if you were scattering pi mesons or protons off a nucleus, some of the nucleons would shadow, would cast shadows, so that the proton might interact fully with the nearest nucleon, but some of the other nucleons farther back would be protected from the scattering. Anyway, you can see from this expression that Jn of z is j minus n of minus z, and this is minus 1 to the n j minus n of z. So this gives us a definition of the Jn's for negative n, whereas the original series expansion did not give us that. We had well, let me actually see what let's just look at that again. Yeah, you see, if you have negative n, that series expansion isn't very convenient because you've got 0 factorials occurring. But this expression, this integral expression, which comes from the generating function, allows you to define Jn of minus z. For n equals 0, it's rather simple, and it's of this form, and in fact, this kind of reminds me of the factor that was effectively a kernel, an integral kernel in the integral equation representation of Bessel functions that we discussed at the end of chapter 8. Anyway, J0 of z is of this form. And you can either use cosine or sine. Now, if you differentiate the generating function with respect to u, and you identify the various powers of u, what you get is you're able to derive a certain recursion relation, and then, of course, typically with these systems of equations, for any of these orthogonal polynomials, there are a gazillion recursion relations. Anyway, you get this one, and then taking the z derivative, you get that one. Now, remember that what the gamma function was, and so you can extend Bessel's equations and the solution to non-integral values of n. we can talk about J nu. And now this is something to the nu. Well, that's fine. But down here, instead of having m plus nu factorial, you use gamma of m plus nu plus 1. And so now this is defined for arbitrary complex nu. Now the self-adjoint form of Bessel's equation is then, if you let z equal to kx, it's then this form here. And this is the form that's often used in problems in physics and optics and electrodynamics. In this equation, in the notation of that we used when we talked about self-adjoint systems, P of x is x, k squared is an eigenvalue, rho of x is x, and we need boundary conditions, and the boundary condition is that this Wronskian should vanish for all functions v in the domain. And the definition of Jn means that J0 of 0 is 1, Jn of 0 is 0 for integers n greater than 0. So since P of x is x, the terms in this boundary condition do vanish at x equals 0 as long as the functions v of kx are twice differentiable on the interval. And to make them vanish at b, we require that Jn of kb should vanish and v of kb should vanish. So kb has to be a 0 of the nth Bessel function. Remember, those are the numbers that the British government classified as state secrets in the 1940s. So the ZNM is the nth 0 of Jn of z. And if we now take k equal to ZNM over b, so that v of kb vanishes, we get Bessel's equation in this form, where k is ZNM over b. For fixed n, the eigenvalue is k squared is z squared over b squared, and it's different for each of the zeros. So the eigenvalue varies with the zeros. And as m goes to infinity, these zeros rise as m pi. And you can sort of see that from the original expression for the approximation for the Bessel function at large values of its argument. Namely, it was 1 over square root of z times the cosine of z minus n pi over 2 minus pi over 4. So what you see there is that to get that cosine to vanish, you need your eigenvalues, your zeros are essentially of the order of n pi over 2. And, well, here it is. It's proportional to that. And so the zeros are m pi plus n plus 1 pi over 2 plus pi over 4. So the eigenvalues are basically m pi squared over p squared. They increase without limit. That means that the Bessel functions are complete, and of course you want sets of functions that are complete. And so then these eigenfunctions then, one for each, let's see what the rest of this thing says, one for each zero are complete in the mean or orthogonal normalizable on the interval 0 to b. The weight function is x, and the orthonormality relation is like this, namely Jn, the two Jn's for different eigenvalues, the eigenvalues being related to the zeros of the Bessel functions, and the weight function being x, we get the orthogonality with delta Lm, and then the overall factor is that. Notice that the normalization constant involves the square of the first derivative of the nth Bessel function at the nth zero of the nth Bessel function. Because they're complete, they then can represent a delta function on the interval, and this is equivalent to things being complete, because if you can express a delta function as a sum of products of eigenfunctions, Jn of one eigenvalue times x of times x, and Jn another eigenvalue times y. There's a prime here that's almost invisible. Then what you have here is delta of x minus y. Actually, there's no prime, that's a y, sorry. So this is the expression for the delta function. If we choose n to be 1 and b to be 1, then this is the sum. And I've plotted in figure 10.2 the sum of the first 100,000 terms of that series for alpha equal to a half, and what you expect then is to get, and y equal to a half, and so you expect to get delta of x minus a half. Notice that this is a highly compressed x-axis. It only goes from 0.499 to 0.501. And on the other hand, the y-axis goes from 0 to 10 to the 5th. And so that's a pretty serious delta function. I mean, a very good approximation. Of course, I only did 100,000 terms. The actual delta function is an infinite number of terms. Some infinite number. So let's see, what did I skip here? So the expansion, the fact that we can expand the delta function in terms of Bessel functions means that the Bessel functions are complete, so you can express any function that's suitably, say, twice differentiable on this interval 0 to b as x to the alpha, and then this sum. Alpha is just some parameter between 0 and 1, and then these coefficients are given by y to the 1 minus alpha times the integrals of f with j. And so you can also consider Bessel functions, of course, on an infinite interval. And if you do that, you get a different orthogonality relation. The orthogonality relation on an infinite interval is that you have to integrate over the eigenvalues in this way. And this is like, I mean, previously we were representing a delta function as a sum of products of Bessel functions evaluated one for each, one product for each eigenvalue. Here, we're taking the eigenvalues to be continuous because we want to create a delta function that works on from minus infinity to plus infinity, and we want to deal with an interval that goes from 0 to infinity. And so that's the analogous expression. And here's an example. I called it Bessel's drum. I don't know why I did that. I thought it was funny, but it doesn't seem funny at this point. I don't know. What do you think? Maybe I should. Well, we've got 3 minutes. Maybe I go through this in 3 minutes. So you've got the top of a drum. It's a circular membrane with a fixed circumference. The potential energy is approximately proportional to the extra area that the surface has when it's not flat, if h of x and y is the displacement in the z direction of the point xy on the membrane, and their derivatives are hx and hy, then the extra length is essentially, of a line segment, it's square root of 1 plus h x squared dx. So that's basically 1 plus, that's dx plus dz squared, square root. And then you do the same thing for y, you subtract 1. So this is the extra area, and so you get a, the kinetic energy is essentially the square of the speed, so it's the time derivative of the height. And then we have here the potential energy is the square, is the sum of the squares of the x and y derivatives of the membrane. By the way, this is really quite an interesting expression if you compare it with the wave operators in quantum field theory or classical field theory. In other words, you have d by dt squared minus the Laplacian. This is just a two-dimensional Laplacian because we're just talking about a two-dimensional surface. But one can wonder whether these equations of theoretical physics refer to possibly something, some three-dimensional analog of the membrane of a drum. And it's that space is vibrating, and that's where that's the basis of the equation. Well, I'm not going to take that very far because A, I don't know how, and B, we're out of time. So, are there any questions? Is anybody starving? I've got extra, okay. I've got extra candy, so. All right, so I guess we can turn it on.